I have the pleasure of introducing Dr. Megan Katsumi, who's a graduate of the Industrial Engineering program at the University of Toronto. She's a research associate at the University of Toronto's Enterprise Integration Laboratory, and she's just recently finished her postdoc at the University of Toronto Transportation Research Institute, so UTTRI, where she worked on ontologies for transportation planning to support the iCity-ORF project. Her current research activities are focused on continued use of technologies of ontologies in asset management and the development of ontology-based standards. And so as we learned last week with Mark Fox's introduction to ontologies, there's an awful lot of the standards effort in that. And I'm very happy to have Megan here to talk about her work with transportation data ontologies. Over to you, Megan.
Great. Thanks so much, Chris. So just get started with a brief overview. So I wanted to talk a little bit about transportation planning, just to kind of give a bit of a lay of the land and talk about what's involved, in particular, just maybe clarifying or making that connection between the work that I've done and that sort of whole subject area and the connection to food and health supply chains, which is the subject of this seminar series. And then specifically highlighting some data challenges in the area of transportation planning. Then I'll be talking a little bit about the ontologies that we developed for that project, or considerable amount of time, I guess, I'll spend on that. And so to do that, I'll talk a little bit more about ontologies in brief, because I think Mark really did a deep dive into that last week. And I'll talk a little bit about the ICD project, about our work in standardization. And then I just kind of want to close out with a specific example of kind of a small application that we worked on to kind of give a more concrete feel for the kinds of things that we can do with ontologies. So, okay, so transportation planning, really we're looking at planning far into the future. And so I'm sort of speaking about this. I'm not really the expert in the domain, but I think I've learned a thing or two in my years as a postdoc. And so really what a lot of the research that goes on in transportation planning is looking at transportation systems over a long time horizon. So, what will the travel demands of the city look like 30 years from now? And how will changes to land use zones impact, land value in 25 years? How will they impact people's travel behavior? So really like long-term questions that are, difficult to answer. And well, ultimately, a lot of these questions and really the decisions that are based on these questions, like, okay, well, should we change our policy on the DVP and things like that? Should we add a new subway station? All these things are public policy decisions that are based on kind of these questions. But the decision making is really supported by research activities, by data collection, data analysis, as well as development of models and simulations in the area. So, and at the end of the day, obviously, we as researchers don't have control over what happens, in the final, with the government. But a lot of the work that is done in conjunction with partners in the city and different organizations to support their decision-making activities to help them better decide what to do. So just a little bit more about what I mean when I'm talking about transportation systems. It includes things like road networks, obviously, which is kind of, I think, the first thing that usually comes to mind for people. The physical infrastructure of the road networks, how many lanes there are, development of new roads, things like that, but also policies. So things like, time of use and tolls and stuff like that. But it also, a lot of the research kind of extends beyond that and looks at things like public transportation, so schedules and routes and management of these services, as well as land use. So things like zoning, what kind of, how tall of a building you can build somewhere, or like what sorts of development you can do in certain areas. And it also ends up looking a lot at the users of the system. So the residents of the city, and a lot of that ends up having to do with like population demographics. You're concerned with how many students are living in a certain area, maybe where people live, where they work, because all these kind of things really influence people's travel behavior and the way that they sort of use the city as a system. So I guess the point I really wanted to make or highlight is that transportation planning results really directly impact the available network for delivery to and access to goods and services. So whether it's food, whether it's health, whether it's education, like all these different kinds of things. So moving on to, I guess, how I got involved, some of the data challenges that we see in transportation planning. Number one, data collection is expensive. So I'm sure, as some of you know, depending on your research area, it ends up being a big portion of any kind of research project a lot of the time. And that's because data is collected either through maybe surveys or studies. All of these cost money, to set up, and there's a lot of time involved. Sometimes you might get data from a third party, which oftentimes you may have to purchase. So that's challenging, obviously. And then a third aspect is that a lot of the times, even after kind of going through, paying, whether it's through your time or actually financially having to pay for the data, there's a lot of integration and cleaning that's then required to, combine these data sets and make it usable for whatever the research question or the, transportation planning question is that you're trying to answer. So that's one difficulty that they're facing. And the next one, or sort of like a following related issue, is that we've found that data preservation is really quite poor in transportation planning in the research across the different research projects. So even though this data is so expensive to acquire, what we found is that collected and generated data is usually stored, and somebody has it once the project's finished. But a lot of times the meaning ends up being lost from project to project. So let's say you have like a PhD student who's doing this research project and has collected all of this data. Once they graduate and they move on somewhere, a lot of the times, you might have all of the Excel files and all the different stuff to go along with the work that they did. But as the years go on, fewer and fewer people will probably be able to understand and actually use that data. So unfortunately, even though the data is expensive to acquire, it's often actually not reused from project to project. And then the other challenge I wanted to highlight, which I think Mark kind of spoke to last week, is that data is siloed. And that's not only, across like between research projects. Unfortunately, we do find that it's siloed even within research groups. It's difficult to actually combine it, but also across sort of research groups in different universities and different cities and things like that. One reason for that is that there's lots of different planning tools and simulation tools that are in use by researchers in different cities. So we have different research groups, we have different data models. So even when this data is actually published, there's no easy way to compare and combine the data because everybody sort of has their own unique data models. So a lot of challenges in the domain. Now, just to kind of, I guess, take a step back forward, I wanted to talk a little bit more about the iCity project. So just been kind of talking about transportation planning in general, but the iCity project, as Chris mentioned, or iCity-ORF project, is how I became involved with transportation planning. And so this was a fair-sized project that spanned a number of years. It involved researchers at U of T, ICAD, and Waterloo, and kind of covered a number of different areas. So it was largely transportation planning sort of focused. So there were projects looking at things like things they call complete streets design. So that's kind of, analyzing a given street layout, how much we only have so much real estate, how much do we dedicate for cars, for buses, for people, things like that. Projects on parking management, transit management, and also these kind of like longer term simulation models that I was speaking about. So all these different kind of research projects, and I was involved in the sort of theme number 1 that we see here, which is related to kind of the data layer that underlies a lot of this work. And more specifically, my focus in the context of the project was to define an ontology that would be able to support data integration across the different projects in iCity. So, just motivated from those data challenges that I spoke about earlier, the question was, can we develop an ontology that will cover all of these concepts and will be able to kind of describe how the concepts in different projects are related, whether or not things can be combined, and support sharing of data between different projects. So I don't know if I can see the number. I think there's a fair amount of repeat attendees to these seminars, but maybe some people weren't here last week. So I do kind of want to go over a little bit what I'm talking about when I talk about ontologies before I go any further. I'll try not to spend too much time on it. I mean, thankfully, Mark did cover this pretty well last week, but I'll go over it, for anybody who may have missed it as well. So when I talk about ontologies, what I'm talking about is sort of a specialized model. And it's this kind of model of a domain that describes the core concepts and properties that span the domain's data. And in particular, it looks like to what extent can we generalize these concepts in a useful way. It looks at what are the key distinctions between the concepts in a particular domain. And it does this through a precise and formal representation that's machine interpretable. So it's not just kind of as kind of schema or a set of definitions on paper. It's something that sort of can be formalized in computer code that can then be implemented in different applications. And so it's more than just a reference model or a vocabulary for a domain. It's something that's formal and supports reuse, validation, something we call semantic integration, as well as inference. So I'll just kind of go through a couple short examples here to kind of clarify. The first is just looking at the definition of a root. So we talk about roots, day-to-day in language, but there's lots of different kinds of roots. In this case, we're looking at 2 different kinds of roots that we could talk about. A simulation route. So maybe in the context of some travel simulation, a route represents a possible path of travel. In that simulation, maybe it begins and ends at some distinct nodes in the network and connects the start and endpoints by accessing some set of arcs. So that's one possible definition of a route. In another application, we could talk about wayfinding service route. So this is, for some kind of map type application. In that context, a route represents a possible path of travel. It has a start and end node. But in this case, maybe we're focused on the associated geometry of the route. So in the ontology, we could represent these 2 definitions in this kind of funny looking notation here. And this is a formal logical definition, more or less, of what we've said in English over here on the left side. So a simulation route has some start node and has some end node and accesses some arc, whereas a wayfinding route has some start node and has some end node and has some geometric shape. And then the key kind of thing to highlight, which Mark was mentioning last week, is that we're distinguishing between these 2 different types of routes, but we're using the same language to do it. So we're doing this in the formal logic, but we're also using kind of these common terms, has start, has end, nodes and things like that. And that's what actually allows us to integrate concepts, different but related concepts, from different domains. Just moving from that to talk a little bit about how these kinds of things can be applied. So we talk a lot about, data silos and the, not being able to understand the meaning of the data or not being able to combine the data. So there are different kind of mapping technologies that exist, which allow us to use the ontology that we've developed to kind of integrate these data sets. So just as an example here, if we had two different data sets, one representing travel simulation routes and one representing wayfinding routes, we could use some kind of mapping technology. There's different options out there, but basically we're defining mappings from whatever the data source is into the language of the ontology. And then we can kind of apply these as sort of rules to either transform the data or to access the data. And that not only gives us the ability to have an explicit understanding of what each of the data sets mean, but it also allows us to kind of access all the data in an integrated way. So in this case, we're mapping ID to a simulation route, start to a node, and so on. And this is just kind of an example rendering of what that would kind of look like conceptually if we were to apply these two mappings and then generate an ontology-based representation of the data. So you can see we have at the top these kind of common set of terminology that's defined formally with the ontology. And then below that, we actually have the sort of instances of those terms that come from the individual data sets. So after applying these mappings, the data is kind of all in one single knowledge graph that we can access in a clear and formal way. Okay, so I hope that's clear. I know questions are at the end. So just coming back to the points that I was making earlier about the applications of the ontology, I talked about reuse and integration and as well as inference. The idea here is now, like taking our example knowledge graph that we've created, all the data that's being now defined using those ontological terms now has its meaning embedded, because we've said that, like this column in the data set corresponds to a simulation route, and we've defined in the ontology exactly what a simulation route is. So the representation actually, in a sense, serves as documentation for how all of the data in the different data sets should be interpreted. Looking at integration, as I mentioned, we're supporting the definition of different kinds of the same kind of concept. So in this case, different kinds of routes. The ontology explicitly identifies how these different kinds of things are related, which then allows us to have a clear understanding of the relationship between the different data sources that we've integrated into this single knowledge graph. So for example, we can kind of ask for any route and its start and end points, and we're able to retrieve information about both simulation routes and wayfinding service routes. And then finally, just looking at using ontologies for validation and inference, the definitions that we've created or that we do create basically capture, in a sense, constraints on each type of route. So data that's defined with the ontology can also be assessed automatically, and also depending on sort of the level of the axiomatization, we can use different sorts of reasoners or rules engines to infer new facts about the data. I'll just leave this up for 1 second, maybe. Okay, so that was kind of the lightning speed primer on ontology. Now that everybody completely understands what I'm talking about, I'm just return to the subject of the iCity-ORF project. So in the context of that project, our role was to develop an ontology. So this kind of formally defined common set of terms that would span the transportation planning domain, or at least the transportation planning domain in the context of the ICD project, and could be used to support that kind of integration for the projects that we're looking at. So the result of that was the ICD transportation planning suite of ontologies. And you can see here kind of an overview of the different concepts and subjects that were covered, in the ontology. So at the lower level, we have kind of the foundational ontologies or subjects So we're defining things like time and location, activities, these really kind of generic but fundamental concepts that are used sort of throughout the domain. Then above that, we have the kind of system characteristics. So we're thinking more the almost like static aspects of transportation systems. So we're looking at, maybe not static aspects, bad word. We're looking at things like buildings and land use, but also population kind of information about people and the households that are comprised of these people. And then beyond that, we're looking at the behavior in the urban system. So specifically focused on the transportation network, but we're looking at trips and travel costs and parking and vehicles and things like that. So towards the end of the iCity project, we sort of had this observation that really these issues that we're trying to address with this ontology are general challenges for transportation planning. And that led to the proposal and the creation of a multi-part set of ISO standards projects for a city data model. So kind of expanding our focus to something a little bit more general, but based a lot on this work, which I'll talk about in a little bit. But before talking about that any further, I think it's really important to start here, which is, okay, so but what about existing standards? Because there's kind of this thing, you know, when you're talking about proposing another standard or another ontology, you get a lot of the times you get this kind of eye roll, like you're just, you know, proposing another standard because you don't feel like using what's out there. But the issue that we found with existing standards, and there are a lot of them out there that are at least somewhat related to the area of transportation planning, is number one with scope limitations. So a lot of the standards that you do see out there, in particular the kind of like implementation level ones, overlap with but don't quite cover a sufficiently broad domain for transportation planning. So data in one standard isn't really easily combined with data in another standard. And then one of the bigger issue, actually, I think, is the issue of encoding limitations. So a lot of the traditional standards that you do see out there are subject to ambiguity, despite having really detailed definitions and detailed documentation. And I'd like to talk a little more about that next. So the example that I'm going to use here isn't like an official ISO standard, but I think it's a pretty good example because it's a pretty good and well-used standard. So I'm not sure how many people have seen this before, but GTFS, or the General Transit Feed Specification, I think it used to be Google Transit Feed Specification, but it's basically a common format that's used for public transit data. And I mean, that's what's used to generate the Google-based information about your transit trips. And it's used by lots of different organizations and lots of different applications. So it's, I would say it's, I think it's safe to say it's highly successful and it's been widely adopted. And it covers things like stop times that we see here, but also transit schedules, and there's extensions I think that they're kind of constantly building on for like real-time data and things like that. And this is just an example of what some of the specification looks like. So in this case, we're looking at an outline of the stop times format, which basically just tells you, okay, you're going to publish your data in, like, let's say a CSV file, and you're going to need to have all these different fields, and it'll tell you if it's required or not and what each of the different fields should meet. But a question kind of arises if you sort of review all the different fields is, okay, so but what about loop routes? So a loop route in this case, we have a simple example here, is a route where instead of going like from A to B to C to D and then backwards, which is what a lot of transit trips look like, in a loop route, you start at A and you kind of go in a loop from A to B to C to D and then to A, and you just continue onwards. So you never sort of reverse your direction. And so it turns out there's actually two different ways that you could represent loop routes. according to the standard specification. So one option would be that you basically represent each stop ID just once. So stop sequence 1, 2, 3, 4. And that's it. So you're going outbound for the first half and then inbound for the second half. And then it's just inferred from that then you start again at 1. Whereas in the second option, you explicitly encode that first stop as the last stop, and it doesn't have a head sign. So this case isn't actually explicitly addressed in the reference. It's something that's identified in a kind of additional document on best practices. And even in that case, it's not sort of explicitly identified which option you should do. It's just they give you the recommendation that B is the sort of preferred way to encode it. So it's a small example, but this I think illustrates a problem in general, a larger problem. So in this case, we can easily end up with different interpretations of the same specification. So this is one of the main issues that we see with traditional approaches to standards. So in the traditional approach, you have really detailed documentation, but a lot of that's done in natural language. Sometimes it's done with formalized diagrams and things like that, but it's often supplemented with natural language. And that's really inherently ambiguous. So you're going to end up with statements where it's not quite clear whether you mean one thing or the other, or maybe you're not quite covering everything completely. They also use modeling languages that tend to focus on data structure as opposed to semantics, and that's what we saw in the previous example. So in that case, we end up with a need for kind of supplementary material to resolve individual issues that may be things that weren't quite clear. And the challenge with that is you can't necessarily predict and detect all the issues. So in this case, they've sort of identified and addressed the issue of loop roots, but it's difficult to say that you've really caught everything, right? So the issue being that meaning is grounded in natural languages, but these differences in interpretation eventually lead to differences in adoption, and that eventually obviously impacts the effectiveness of the standard. If you have people interpreting in different ways, then it doesn't quite work. Right? So all this kind of leads to the idea of having an ontology-based standard, in this case for transportation planning, as I was sort of alluding to before, and in general for the city domain. And that's because, as we've sort of talked about, ontologies provide a way to address these challenges, as well as the limitations of traditional approaches to standard specification. And that's because in the formal logical way that they define the terms, there's a unique interpretation and explicit and unambiguous encoding. So you can kind of identify these incorrect or correct interpretations automatically. And there's also no question about whether something conforms to or doesn't conform to the definition. It's also nice that they have these added benefits of working with different tools and different formats, and being able to support these other types of applications like reasoning. So this is all kind of leading to, I guess, also highlighting some of the work that I'm involved in, as well as Mark right now, on a kind of continuation of the standards effort. So following from the iCID project and the kind of recognition of maybe that this is something that should be standardized, we proposed a series of these standards projects, which are now approved work items within ISO IEC. And they're basically defined in, broken up into different parts. So 5087-1 is the kind of foundational concept, similar to what I had shown previously for the iCID project. And then this second part is what we call the city level ontologies. And that's really looking at the concepts that cover the city domain and are sort of generic and broad enough that they'd be used by lots of different applications that have something to do with the city. Excuse me. And then beyond that, we look at the service level. So the idea is basically you have parts 1 and 2 of the standard, and then it's going to kind of grow from there, part 3, part 4, part 5, and so on, looking at different city services. The first one being transportation planning, but you know, potentially looking at things like you know, shelters and like education and different subjects like that. So yeah, so that level is comprised of multiple standards, and the first one we're looking at will be transportation planning. And this is just an example, but it's probably not quite accurate anymore because we've been going through some revisions through the ISO process, which is another benefit of that. You get a lot of you know, feedback from people involved in different standards and different applications and things like that. Okay, so I'm still okay for time, I think. So at this point, I kind of want to switch gears a little bit. I talked a lot about ontologies for transportation planning and standards in general. And now I'd like to talk a little bit about a specific project that we worked on in the context of iCity. And this is work that was done by myself, as well as Hassan Bayanini, who's another student or another postdoc that was involved in the ICD project. I think he's still involved at work at UTTRI, as well as 2 other individuals from Esri Canada, so Tasso Stardust and Michael Leahy. Okay, so talking about data challenges again, specifically in the context of this project, we're working with Esri Canada, so we're looking at data issues, not just for transportation planning, but for geospatial information systems. So there's a lot of the same problems, but some more specific characteristics come about, in particular looking at data silos. So when we're dealing with GIS systems or geospatial information systems, all the data that you're looking at is basically location based. So everything is kind of done in the context of a map. So you have kind of spatial relations between anything that you're looking at, but any object that's represented on the map doesn't really have a connection between its attributes and the attributes of anything else. And because of that, it's really difficult and time consuming to perform complex geospatial queries, because it basically involves you having to figure out whatever the logic is to kind of combine different layers of information about objects. So whether you're looking at like zones and buildings or whatever it is, and figuring out what the different attributes are that you also want to kind of refer to. So this results in missed opportunities to combine. It also results in missed opportunities to combine geospatial data with other data sources, as well as just combining the data, you know, across different geospatial data sets. So in this project, we're basically looking at creating a proof of concept that would support querying the GFX. GFX is GeoFoundation Exchange. A little bit more on that here. There's an excerpt that I sort of snatched from the Esri website talking about base mapping. So base mapping is needed daily to support coordinated planning, analysis, and operations of activities across almost all sectors of Canadian society. And they talk about how all these different areas all need a modern shared mapping to function as efficiently and effectively as possible. The GFX is a national collaborative open data exchange for accurate and authoritative geographic-based mapping data. It's designed to facilitate coordination and modernization of Canadian-based mapping. So base maps are basically reference maps that you can use in these systems to overlay data onto. So you have a base map, and then you'll have your data set of whatever it is, like parcels and things like that. And you can lay that data on there. So it's obviously really important when you're doing any kind of application to know that you kind of have a common reference map, that you're looking at the same reference map as somebody else in another municipality. And the idea is GFX kind of is one component of supporting the goal of having this kind of common map across Canada. And they're looking at integrating municipal, provincial, and federal data, and the GFX kind of provides sort of a framework that they're using to create this. So because we're working with Esri, we kind of decided to start our focus there, looking at these GFX data sets. And we just started by looking at a really simple case study. So given these GFX data sets, which give us things about road networks, neighborhoods, and things like that, let's say identify the points of interest, neighborhoods, and land use types along some shortest path between 2 points over the road network. So points of interest, neighborhoods, land use, and road networks are all different data sets that are published by the GFX. So you can imagine a really simple algorithm that could achieve this, could achieve this task, where you basically select origin and a destination. Through some kind of tool, you're going to find whatever road segments identify the shortest path. And then given that path, you identify the neighborhoods, identify the land use, and identify the points of interest that are near or intersect that path. But the issue, as I mentioned, is with data silos. So we have all of these different data sets from the GFX, but they're not connected. So we can select our origin destination. We can use Esri tools to find the shortest path. But when it comes to kind of addressing those last parts of the question, road segments are not connected to neighborhoods, road segments are not connected to land use types, and they're not connected to points of interest. So it makes the whole thing a little bit more complicated. And this is going back to that issue that we talked about at the beginning, where now we would have to kind of create these complex queries and implement them into whatever tool in order to address this use case. And then even then, that would just be a solution for this use case. And if we want to answer any other questions, we'd have to do the whole thing all over again. So the idea was to use ontologies to simplify the problem, or at least we're really, in this case, investigating the use of ontologies in this general framework to see how it works. Then we're using ontologies. We're really kind of assuming we have this common set of concepts and relationships between them that we can use to answer these three questions. And by essentially describing the structure of knowledge in the GFX. So imagining we have this kind of standard formalism that describes road segments and how they can be related to different sort of features or areas on a map, things like land use and points of interest in neighborhoods. So in the project, we developed kind of a small extension of the iCity ontology to represent the concepts in the GFX. And that essentially gets us a framework that we can use to develop a knowledge graph of the GFX data that we're interested in. So in this case, we have the iCity terms of feature, which is basically some area on a map, and land use. And then we can extend these concepts with the GFX specific terms like point of interest, neighborhood, and road segment, and the different sort of attributes that go with those. So we use that kind of small extension to support the development of this prototype, which is essentially a GFX supported routing tool. So in the prototype, which is just kind of a screenshot of one of the iterations, you select an origin and destination, and then it kind of uses some of the Esri tools to figure out what that shortest path is, and then figure out what are the road segments that make up the path. And then you basically use those road segments to query an ontology-based representation that has the relationships between the road segments and the neighborhoods and the points of interest and things like that. So it's a relatively small application, but the idea was really to kind of demonstrate how ontologies could be used in the context of these geospatial information systems tools, and kind of explore what that architecture would look like and what the kind of opportunities would be after that. So I guess I just want to kind of finish up by talking about some of the future work that could happen in this vein. As far as I understand, I'm not involved in this project anymore, but as far as I understand it, there will be, or there's a potential for some follow-up projects. So some things would be to explore other sorts of queries. We looked at really kind of basic ones to do with a particular route, but you can imagine we could look at different types of points of interest. In particular, we could look at neighborhoods with either the most or the fewest paths between, like, let's say, residential areas and the healthcare providers and things like that. So there's a lot more that I think could potentially be explored just in the context of the GFX data set. There's also opportunities to kind of continue on improvements to the design and functionality of the prototype, obviously. And also there's other use cases in general that this same kind of paradigm could be applied to. So at Esri, there's also a lot of work on, or at least at the time of this project, there was a lot of work being done on what's called the Next Gen 911. So kind of developing a new system to support 911 dispatch, and having a sort of integrated representation of the geospatial information, as well as the ability to kind of integrate external data sets, is something that we thought would be very useful for that. And another thing which came up was actually just the use case for data validation in the context of the GFX. So just in doing the project, we noticed a lot of, incomplete fields and things that didn't quite make sense, where you could imagine just by applying, by developing these definitions and applying them to validate the data that's being submitted for this kind of common base map, you could get a lot of value out of that as well. So that's kind of covers everything that I wanted to talk about today. I think I'm okay for time. So I'll turn it back to you, Chris.
Okay, great. Well, thank you very much. I think you covered a lot of stuff, and we have time for questions. And so I want to open it up. If somebody, you can raise your hand, or you can type something in the chat. Anybody have a start question for us? So I had a question about, I guess this is more related to the city ontologies that you talked about. And I guess one of the questions I have is, how does that relate to rural areas, right? So to the extent that the ontologies are developing ideas and notions and concepts that are relevant to cities, is there the expectation that these can be applied to rural areas, or that another ontology will have to be created, or a branching combined ontology if you try to address the issues that are more rural and remote areas? Can you comment on that at all?
Yeah, so I think I don't think there's an expectation that it would be maybe directly applicable. I think that there's definitely, if we were to shift our focus into a rural context, we would definitely find that we probably missed, certain concepts that are more relevant in rural context than in the municipal, like an urban, like big city kind of context. But that being said, there's still these sort of foundational concepts. There's still going to be a road network. There's still going to be parcels of land where you're interested in, what's the land use and land cover like, and things like that. So I think a lot of the common core should be unchanged. It's just a question of maybe specialized extensions of certain terms that will be more relevant for rural applications than for urban applications, and vice versa.
Right. Okay. And I see, Arif, you have a question?
I do. Hi, thanks for the presentation. It was fantastic, actually. So my name is Arif Rafiq. I lead the transportation practice at Esri Canada. I'm also leading the evolution of the GFX that you talked about to the more transportation-focused transportation geo-exchange. And so I just learned the word ontology about 4 weeks ago. I didn't know that word existed until then. It was actually Mark Fox that I learned about it. And I've been trying to understand how ontology can be helpful for data integration specific to transportation. And so I'm watching your presentation and I don't know, I'm struggling to understand this aspect of it. And if you look at, one of your older slides, your earlier slides, it talked about nodes and the connections between those nodes. And you were giving an example about wayfinding. And I think if you think about a municipality and you're doing some wayfinding analysis, it might be intuitive to think about nodes as street intersections, and then the passage or the traversal between those nodes as the street segments. But then if you look at like pavement management, for example, at that same city, they might consider a node being the beginning and ending of a paving project, let's say, and that may not align street segments. And the name of that paving project might be a project number rather than a street name. And even if you look at GTFS, the nodes are bus stop locations. The traversals between the nodes may not be the streets themselves, it's not some other ID. And so I'm trying to understand how ontology can help us understand that, a wayfinding route actually goes over the same piece of road that a paving project was done, 3 years ago, which happens to be the same piece of road that the transit system is going to be putting a new route on. How does ontology help us understand that those three things are actually talking about the same piece of road?
Yeah. So I think there's kind of a couple issues in the example, and it's a great example that you've given. And so some of it, I can tell you that ontologies kind of help to address this idea that, okay, so the GTFS nodes are bus stops, but wayfinding nodes are intersections, and then like project nodes are something else altogether, right? So the point of ontologies is in actually explicitly saying, well, okay, let's just say none of these are nodes. Nodes are something else, and then we can actually specialize according to each of these applications what we're really talking about. So in these cases, in a lot of these cases, you're kind of talking about points maybe on a road segment, which may be distinct from the kind of nodes like wayfinding nodes, but you can use the terminology of the ontology to sort of either identify explicitly what the relationship is, if there is one. So in this case, maybe they're all points on a road segment, but they're different kinds of points. And also just distinguish when they're totally different things. But in terms of actually figuring out, that this paving project is on this road and stuff like that, I think there's definitely more to it than that. So in some cases, you'll still need some degree, at least from my experience in some of the projects that we've looked at, like you still need some degree of other sort of tool support, like let's say to compute the intersection or, figure out, because everything's going to have different identifiers as well. But what happens is it's kind of like a combination of tools to maybe figure out that this project is dealing with a segment on, on this road, which is also the same road that's, being referred to in some wayfinding application. But then you can still use the language of the ontology to kind of describe that this paving project is contained in or intersects this other road. So you still have this way to kind of connect everything in such a way that you could query everything and kind of understand what you're referring to and have access to all of this kind of information without any kind of confusing. So it doesn't 100% solve all the integration issues. There's still definitely going to be issues that you need some kind of other tool support, I think, to address.
Thank you. That's very helpful.
Okay.
So maybe I can ask a question. I see Arnush has a question. I'll get to her in a second. But with respect to exactly the question that you just answered, it seems to be that we have a bunch of different systems that are, for example, all using node to refer to something in their system. But of course, the nodes don't mean the same thing. Mm-hmm. And is it the case if I was going to apply ontologies? So if I have a general ontology like you've suggested, what I would have to do is I would have to kind of take each of these systems and define them with respect to this ontology that you've defined. And once I have each of these systems defined within the ontology, that allows me now to tie these things together and do some of that reasoning. Is that kind of the process that I would have to go through to enable that integration?
Yeah, exactly. And so that kind of gets you like that kind of hub and spoke model that you see sometimes. But the idea is that from any system or any data store, you would or somebody would have to go through the effort of creating that kind of translation. And that's, there's sort of formal languages that you can use to make that explicit. The pro of that is that basically, so you're not saying, here's my standard ontology, everybody has to use these terms now. Everybody can still stick with, call your nodes nodes, and that's fine. But somewhere there's going to be this document or this piece of code that says that the wayfinding node is referring to this, whereas the projects node is referring to this. And then that all connects to that single kind of unified representation.
But wouldn't that depend on the nodes still being defined? I'm thinking of examples where there may be arbitrary nodes and nodes are not clearly defined.
Yeah, so I mean, and those issues kind of go beyond, like at some point somebody would have to commit to what the definition is for this to work. So a lot of times, like even going through that effort uncovers issues in the data. Like there's some field here and it's kind of ambiguous, or maybe it's used in multiple different ways. So in order for the effort, the integration effort and the formalization effort to be effective, at some point that distinction, I think, kind of needs to be made. Yeah.
Okay, thanks. Arnush, you had a question?
Yes, thank you so much. It was a great talk. This topic is also new to me, so maybe my question is a little bit basic, but I was just wondering, like the logic behind defining this knowledge graph. Is it to use any type of graph-based algorithms on it, or maybe finding, maximum degree node? Is there something like that in this context?
Not in the context that I've looked at. I think there's some connection to work that's being done with graph databases, because I know that there's basically they have kind of their own set of rules, and there could be some correspondences that you could sort of identify between those sorts of rules and the way that those are implemented and the formal rules that we're talking about here. In general, at least in the realm that we look at in our research group, the logic that we're looking at representing ontologies in is either based on description logic or OWL, which is kind of the web ontology language, and that's kind of underlying a lot of stuff that's being done on semantic web. And the reason for that is just because that's kind of become sort of the de facto standard, so there's more support for that. And then first order logic, because it sort of gives you more expressiveness. But yeah, languages end up becoming a big thing, because then there's like all these trade-offs for what you could do in one or what you can do in the other, and the expressive abilities and things like that.
Great, thank you.
No problem.
Any other questions? We've got maybe time for one more if somebody wants to sneak one in. So I had a question with the GFX, and in particular the last example, and relating back to some of the discussions I've had with Michael about food deserts and the fact that the geographers don't like food deserts anymore. And my understanding is that part of that was that it was much too simple a concept to sort of look at a part of the city where there are no healthy food stores, for example, because it's not taking into account the transit structure into that area. It's not taking into account the demographics, the socio-demographics of that area. And so in fact, access to healthy food is much more complicated than just figuring out where your grocery stores are. And it struck me that the type of example you just used with the wayfinding and the neighborhoods along the way is kind of exactly what you would like to do to integrate the data to get a richer idea of the type of access to food in a particular neighborhood. And so I guess this is a question for both you and Michael. Am I out to lunch? No pun intended, to say that there's a connection there?
Well, I'll go first. I don't think so. So that's actually kind of what I was. So in presenting this, I'm also trying to kind of keep the theme of the seminar in mind, and that was something that I think really we kind of could come up with lots of different interesting applications. Just in the context of our prototype, we really scaled it down, but that would be the idea behind, I think, bringing in these other sorts of data sources, because then you could look at these kind of more complete representations of those sorts of questions, like incorporating the transit route structure as well as representations of neighborhoods, and then maybe you're bringing in census tracts and things like that. That was my, but I'm not an expert in that part of the research, so I don't know.
Maybe I could offer.
Yeah. Oh, go ahead.
Oh, sorry.
Yeah, I'm here. That's okay. I'll be quick. I mean, I agree. I think that's a good response, and Megan, and it does allow for a more nuanced take. But I think the thing that I always struggle with this sort of ontology framework is that it's while it is flexible, it's still really rigid, and it sort of doesn't always allow for like the quick adjustments that may be taking place in social systems that sort of emerge. And I guess you could kind of take that into account, but it just feels like too complicated then, that the framework kind of falls apart at that point. But that's just my impression. I don't know if that makes sense at all.
I think there's definitely still probably improvements to be made in the sort of, I would say, the usability of ontologies. Like that's something that comes up, and I can kind of speak generally about that in some of the projects that I've worked on. You can spend a lot of time developing the common core and the foundation and things like that. But at the end of the day, if I'm not staying with the project, whoever is going to be kind of updating and continuing to like maybe tweak the ontology needs to be able to do so in an efficient and effective way. So as where maybe like, for me, I'd say, oh, it's no problem, I'll just add in this concept. It becomes something like you want it to be as easy as possible for somebody who's not an ontologist to kind of make those adjustments and kind of continue to evolve the ontology. And I think that's something that's still kind of a challenge in the domain.
Yeah. There's the XKCD comic. I don't know if you've seen this one where they say there's 14 standards. We need one standard to unify them all, and then it says later on 15 standards.
Exactly.
All right. Well, I think we're at the hour, over the hour. So I wanna thank Megan for a really great talk, and can you join me in thanking her?
Thanks.
So we have a
pleasure.
talk next week as well, and this is going to be a talk by Joanne de Zeger from MIT, who's going to be talking about her work on supply chains, and in particular on algorithms that optimize informal supply chains. And from some of the discussions I've had with her, it should be a very interesting connection with some of the work that Ryan has done, because she's looking at some of the food supply chains in some of these developing countries, but from a very engineering perspective. And so I'm hoping we're going to get a good conversation going next week, hopefully as good as this week. So thank you again, Megan, and hope to see you all next week.
Thank you.